Welcome to the Quantum to Cosmic YouTube channel with me, Ollie. Welcome back to this tutorial series on functions. This series is aimed at first year undergraduate university students or those who are just interested. Whether you just need a refresher on the topics or are learning them for the first time, you're in the right place. Today we are continuing with functions and limits, looking at common functions you might come across. So if you're ready to learn, then let's get into it. Now, let's explore some common types of functions you might encounter. First are polynomials. So a polynomial function is a sum of terms consisting of a variable, in this case we'll use x, raised to a power and multiplied by a coefficient. And so that is of the form y equals a0, so the coefficient of x to the 0th power, which would equal 1, so we won't write the x, plus a1, where x is to the power of 1, plus a2x squared, and so on, until we get to an and x to the power of n. And we can write this in a shorter form of the sum from r equals 0 to n of ar x to the r. N here is always known as the degree of the polynomial. So n always equals the degree of the polynomial. Next, let's talk about linear functions. So these are polynomials of degree 1, and that is meaning the highest order of our dependent variable x is only to the power of 1. So it would be of the form y equals a0 plus a1x. And this graph here represents this function, and our intercept will be a0, because when x is 0, we have only y equaling a0. And the gradient of this slope will be equal to, so this number over this number will be equal to a1. Our y divided by x, ignoring this intercept value, is going to be a1. You might recognize this as y equals c plus mx, or y equals mx plus c. That's how I learnt it at school, and m here is the slope and c is the intercept. Now let's look at quadratic functions. So these are polynomial functions of degree or order n equals 2. So from the equation of a polynomial above, we know that it will be y equals a0 plus a1x plus a2x squared. And these will look similar to the graphs that I've plotted on the right. When a2 is a positive number, it will look like this smiling mouth, whereas when a2 is a negative number, it will look like an unhappy mouth. And the way you can try and remember that, if you're trying to draw them, or you see a graph and you need to know which way around a2 is, whether it's positive or negative, you can just remember positive means that it will be smiling, whereas negative will mean that it's pulling a frowned face. So negative for negative, positive for positive. Now let's look at power laws. So we could write this of the form y equals a x to the alpha. And this a is technically a of alpha, like we had a1 for x to the 1. And we're assuming that a alpha is not 0. It's a positive number as well. So alpha here represents the power, or we could also call it index or exponent. And if we differentiate this power law, so dy by dx, we would get alpha a x alpha minus 1, x to the alpha minus 1. So we'll go on to differentiation later, but this is the result we would get. And these basically would look of this form. So when alpha is 1, we would get this just straight line. It would basically be our linear function as before. Whereas if alpha is between 0 and 1, we would get this tailing off. And if alpha is above 1, we'll get this keep increasing function. And this point here where they all intercept would be the point 1a, because when when x equals 1, y equals a for all whatever alpha is, because 1 to the power of anything is always going to be 1. So functions that are used throughout physics are the trigonometric functions. So these would include the sine x, cosine x, tan x, etc. And these are used throughout physics, and similarly the power laws are used throughout physics. So try and get familiar with these if you're not already. They'll be coming in handy a lot throughout this course. Next, let's look at the Heaviside or step function. So we write this as h of x is equal to, and then for the graph on the right, it's going to be 0 for x is less than 0, and 1 for x is greater than or equal to 0. And this function is discontinuous at x equals 0, and this means that when we differentiate dh by dx, we'll get 0 everywhere except for x equals 0. So an example of where this might come in handy is when you're trying to have the function equaling 0 until you want it to switch on. And the example I've given here is the Heaviside function times by a sine function, and the x minus 1 here represents how it will carry on past 0, it will go until 1. So Heaviside is going to be switching at 0, so when x is 1, this inside of this brackets will be 0, and that's why it will switch on at that point to equaling 1 as it is up here. So then we'll have 1 times by the sine function, and it will continue making the sine. So it will have this useful property which it can switch on a function at a given x value, whatever you want it to be. So for the modulus function, we write it as x with these straight lines on either side equal, and it's similar to the Heaviside function, but instead of equaling 0 or 1, it will equal x and minus x for x is greater than 0 and x is less than 0, respectively. And that will produce a graph like this, where it sort of looks like it just bounces up and its gradient is 1 in this example. I know it doesn't look it, but it's meant to be equivalent. So if that was 1, this will also be 1, and then this will be minus 1. So you can see they both get to 1 at minus 1 for the minus x, or 1 for the x. Next, let's discuss even and odd functions. So for an even function, we can say f of x equals f of minus x, i.e. it's symmetrical around the x equals 0 line. And the example I've given here is the f of x equals cosine of x, which is symmetrical, as I was saying. Whereas for odd functions, we would say f of x equals minus f of minus x. And the example here is f of x equals minus sine of x. And this is sort of the opposite, where it's sort of mirrored across the origin. And these definitions aren't always applicable to all functions. So not all functions are odd or even. An example of that would be x plus x squared. I've drawn the plot for y equals x plus x squared here on the right, and as you can see, it doesn't really fall into the odd or even category. So as you can see, not all functions are odd or even. A useful tip to remember when multiplying functions together is that an even function times an even function is going to result in an even function. Similarly, an odd times an odd will result in an even function. And then an even times an odd or an odd times an even will result in an odd function. And I sort of remember this by thinking of positive and negative numbers. So a positive times a positive is a positive, a negative times a negative is a positive, but a positive times a negative or a negative times a positive will result in a negative number. And it's sort of a useful tip to remember when trying to imagine these functions or plotting them in general. A general function g of x can always be expressed as the sum of odd and even functions, and we can see this by considering splitting g of x into a half g of x plus g of minus x plus a half g of x minus g of minus x. And if we times this out, we can see these g of minus x terms will cancel and these g of x terms will add together to make our full g of x. And by considering what we've said before, we can clearly see that this part is an even function and this part is an odd function. And so we can always see that any general function can be split up into an even and odd functions added together, and sometimes this odd function will be 0 and it will be a fully even function. If we look at that example we had before, x plus x squared is clearly an odd plus an even function. Y equals x is just a straight line, which you can see is going to be odd. It's f of x is f of minus f of minus x, and then x squared is going to be even by looking like this, roughly, and then f of x is just f of minus x. It's symmetrical. The last thing I want to say about even and odd functions, which is a thing used all the time in physics, is if we have an even function, f of x, when we integrate that between minus a and a, let's say, we will get 2 of 0 to a of f of x, seeing as it's symmetrical. And this helps massively when trying to work out integrals. And similarly, probably more useful, is being able to see that for an odd function, the same integral will always equal 0. And that's just naturally by looking at a odd function. This integral plus this are going to cancel out because for an integral it's going to be negative adding to the positive of the same area, so they'll just cancel out, whereas you can see these are just going to add together and be the exact same, so it'll be twice as much for an even function. And so it's just a very useful thing to remember, especially this odd one. So let's talk about inverse functions. For a function y equals f of x, we can sometimes invert this to give x in terms of y, i.e. x equals g of y, where g is the inverse function of f of x. And we usually write the inverse of f of x as f to the minus 1 of x. And an example of this could be f of x equals x squared, and that would lead to f to the minus 1 of x equaling root x. And for all functions that have inverse functions, if we write f of f to the minus 1 of x, so f of x acting on the inverse function of itself, that's the same as the inverse function acting on the function of x, and that will always equal just x for all x. And if we use our example, we can see if we put in here, so f of x is going to be x squared, and on the inside f to the minus 1 of x is root x, and that equals the same as the root of f of x, which is x squared. You can see both of those are always going to be x, no matter what x is. So we can extrapolate this and see that it will work with all functions that have inverse functions of themselves. Similar to what we had for inverse functions, where we can have a function acting on its inverse or the inverse function acting on the function itself, we can also have a function acting on another function. So for this example, f of x equaling x squared and g of x equaling sine x, we could write f of g of x, and substituting in, we would have x squared and then g of x being sine x, which would be sine squared x is how we write that. And you could also have g of f of x, which would be sine of x squared. And clearly these are different things, and so they're known as non-commutable, or they don't commute. And this is important because the order in which you have these functions acting on one another is important. So I'll draw those for you now. So as you can see here on the left, we have sine squared x, which is f of g of x, and on the right we have g of f of x, or sine of x squared, and these clearly look very different, and as I was saying, they don't commute, so the order in which you have these functions acting on each other matters. For our final of the common functions, we'll be looking at the many-valued function. So as you can see here on the right, this top figure represents y equals sine of x. And if we just look at any x value, say here, it's going to have just one y value, or over here, there's just one y value. And we write this as for each x, there exists only one y. And as I said it, this means there exists. And so this is just a normal function. It has one value for each x value. So the opposite end of the scale is the many-valued function. So if we look at the inverse function of sine of x, so the inverse would be sine to the minus 1 of x, and this does not equal, just as a side note, sine of x to the minus 1. These are different things. That would be that, which is not the same thing. And sine to the minus 1, this is the inverse, and it looks like this plot over here. And if you look at this, we can see that for every value between minus 1 and 1, every x value will give an infinite number of different y values representing each x value, and that is what a many-valued function is. Therefore, because there's infinitely many values for this, we define a principal value, a sort of range of values. So for sine to the minus 1 of x, we have the domain minus pi over 2 is the values that it can take up to pi over 2. And that is for minus 1 to 1. So if we looked at that, it will be from this point to this point. And you can see these are only going to have one value. And that's our principal value domain. And similarly, we can have one for cosine to the minus 1 of x, where that's from 0 to pi. That's similarly for minus 1 to 1. Today, we've looked at some common functions that you might come across in your studies going forward. In the next video, we'll be discussing logarithms, exponentials, and hyperbolic functions. So if you want to learn some more about that, join me in the next video. If you learnt something new or just enjoyed this video, please hit the like button and don't forget to subscribe and tap the notification bell to stay updated on new videos. In the meantime, stay curious and I'll see you in the next one.